Okay, last topic that we need to go through for this unit is about the Doppler effect or the Doppler shift. Recording this one a little bit differently. We're kind of running out of time as to the recording on this in terms of when we're taking our test. So there's no notes to take with this. However, it would probably be good maybe if you write some things down or just a couple of definitions, because what we're going to be talking about is, again, the Doppler effect. And you've experienced this. This is when you have noticed something going past you, or a siren, or cars, where it kind of makes the sound of yow. And hopefully you're listening to this, because if you're not, of course, if you're not, you have no idea what I'm saying right now anyway. But there's no words on the screen today, so probably want to listen to this. So Doppler effect, one more time. Meow. I know you'll hear me do that a number of times. But if you think about what that is happening, the way that that is, it's a pitch that's going up, and then it's a pitch that's going down. So as an object is moving towards us, our brain is thinking that the pitch is rising, in other words, getting higher. As the car or the object goes past us, our brain is registering it as the pitch getting lower. So I want to use this gizmo to try to show you visually kind of an explanation of what's going on with that. We've got an observer in the middle, and we've got a car. And as we start pushing play, this car is going to move, and I'm gonna get it to move for a minute, and then I'm going to stop it, just so we can kind of look and see what's going on. So I'm gonna stop it right here, and you can see the circles are coming out of it, and the circles are supposed to be representing sound waves. So the car is stopped, and imagine if you're sitting in the car, what the car sounds like is meow. It's going to be a constant pitch. It shouldn't be going up, shouldn't be going down. And if you're in the car, it doesn't matter if you're moving or not. That's what you hear, because you're moving along with the car. So the person's standing over here in the grass right now, because the car is not moving, should be hearing basically the same thing as the person in the car. The frequency is the same. So remember that frequency and wavelength are related. The red lines are to kind of represent a wavelength. And if I pause it, you can get to see the idea that the distance between red lines, no matter where you go, is basically the same distance. So the wavelength is the same distance. If the wavelength is the same distance, then the frequency is the same distance. And if the frequency is the same, then our ears and our brains should all be hearing the same thing. Now, what happens though is when the car is in motion, these circles change a little bit. Now, the car continues making the exact same circles, but what happens is every time it makes a new circle, it has moved in relationship to its previous position. And so it's not just like you're tapping on water and you're getting circles that are perfect circles inside of circles. You're tapping and moving to the side. So effectively, you're chasing one side of the circles and running away from the other side of the circles. And it's a little bit easier to see if I speed it up a good bit. That turned it into an airplane. I'm not quite ready for that one yet. So I'm going to hit play, and then I'm going to let it move for a moment, and then I'm going to pause it, and hopefully we can see this difference that we have here. So if I pause it now, notice the circles. It's not perfectly easy to see. It'll be easier to see with the airplane in a moment, but the distance between the red lines or the red circles in front of the car is a good bit smaller than the distance behind. In fact, we can actually measure it with a ruler. So in the front, you can see now the wavelength goes from about 0 to 500, whereas in the back, the wavelength goes from about 0 to 900. So the waves are shorter in the front, and the waves are longer in the back. Now, again, the car was making the same waves, but the fact that the car is moving changes how close the waves are in the front now, and it changes how close the waves are. Actually, it changes them all over the place. So if you're an observer in the front, so this person's over here, they're going to be experiencing waves that are closer together. Therefore, their brain is going to experience a higher pitch. If the person was in the back, their brain is going to be experiencing waves that are farther apart, which is a lower frequency, and their brain is going to experience a lower pitch. And so this kind of is the phenomena, the explanation of why when we have an object that's approaching us, the sound appears as if it's going up higher. And when the object is moving away from us, it appears that the sound is going out lower. Again, this is a little bit easier to see if we turn this car into an airplane. And we'll move the person back over here. And so when I hit play with this, it's really easy to see with the airplane now, because it's going so fast in relationship to what we would normally experience. that its sound waves in the front are incredibly close together, and the sound waves behind it are incredibly far apart. So again, if you're a person in the front and you're hearing this airplane, what you're going to be hearing is a really high frequency sound because the waves are so close together. Again, remember, a wave is generated from a vibration, but since this airplane is moving towards you, it's as if the vibrations were happening faster and faster, with more frequency. If you're in the back, now notice how far away each wave ends up being. So again, the wave itself is the same wave. It's making the same circle every time. It's just that when it made this circle, it was in the middle of the circle where the arrow is. When it made this circle, it was in the middle of that circle. So again, the circle just continues to generate normally, but every time there's a new circle, we're in a slightly different position. So you'll see that the airplane is almost going as fast as the sound waves that it generates. And in fact, you can get an airplane going basically fast enough that it's approaching the speed of sound. In this case, it actually is going faster than its own sound waves, which is what causes a sonic boom. And we normally don't have the pleasure of being able to experience those, right? So again, if the airplane is just sitting here not moving, or if the car is just sitting here not moving, there is no quote unquote Doppler effect, because no matter where you are, you're experiencing the same wavelength. And if you're experiencing the same wavelength, it's the same frequency. And if it's the same frequency, then you're hearing the same pitch. So you'll notice the number up here again, as I start having the car move a little bit, you'll see the frequency to the observer is going up. And then if I put them back here, it was less than 500. So in front of the car, it's going to be greater than 500. We put it back here, it's 500 exactly. And then if we stop the car again, it just goes back to 500, which is which is basically the frequency that the car is actually making. Okay. So one more time, the Doppler effect is the perception. Okay, it's not a real, but it's a perception of an increased frequency of an object, or the sound of an object, due to the object's motion. Again, so if it's moving at us, it appears that the frequency goes up. If it's moving away from us, it appears that the frequency goes down. And again, one of the main misconceptions that people often have with this is that it is volume. And the Doppler effect has nothing absolutely to do with volume. It's not how loud or how quiet the car is. Now, obviously, if something's getting closer to us, it's probably going to sound louder. If it's moving away from us, it's probably going to sound quieter. But that has nothing to do with the Doppler effect. The Doppler effect is all about frequency, wavelength, and pitch. So if you don't write but one thing down, let's write that down, because probably in the video at this point, I'm going to ask you to explain real briefly in 2 to 3 sentences, what is the Doppler effect? And again, it should be the apparent change in the frequency of a sound due to the motion of an object. Again, as we're moving closer to something, the apparent frequency is going to get higher, so the apparent pitch is higher. As we're moving away, the apparent pitch and frequency is going to get lower. That's it.